So let's continue with organic chemistry. And this, I believe, was one of the last slides we saw last week. So we're going to try to explain what is an isomer, right? So if anybody didn't print out the slides, I'll show them where they can get it after class, right? So what is an isomer? Well, to keep it simple, right? This means if you take an organic compound, I believe last week we did something called alkenes. Let's say we mix up or rearrange the carbons and hydrogens, right? So we take all the carbons and hydrogens and we rearrange them in the same pattern, right? So they have the same amount of carbon and hydrogens, except they just joint up differently. You call that an isomer. Now that sounds a little bit complex. I guess you probably need to see an example of exactly what an isomer is. Usually nobody ever understands what an isomer is unless they see an example. So let's just go to the next slide one time. This here, I'm going to circle this organic compound. I just circled it. I want you all to quickly name that for me. Send the name for that organic compound on the chat for me, right? What is it? Right? Get involved, guys. Just don't sit down and get involved. Correct. We know this is an alkene for sure because it only has single bonds. So last week I showed you something called double bonds, and this one has no double bonds. It's just single bonds. It has how much carbons? 1, 2, 3, 4, 5, 6. Now this is a straight alkene. It has no branches in it. So his name is hexane. And remember, all alkenes obey this formula. Remember the formula? CnH2n plus 2, right? And you notice it has what? How much carbons? It has 6 carbons. So using the formula, 2 by 6 is 8. 8 plus 2 is what? 10. You all remember that you call this the molecular formula. I have to do a little bit of revision from last week. I know it's a lot to take in, right? Someone said I made a mistake just now. I think I did, right? 6 by 2 is what? 6, I made a mistake. It's 6. So 6 by 2 is 12 plus 2 is 14. Hey, how come only one person corrected me? All right, only one person. That's a huge mistake, even for me to make. Okay, so the thing about it, if I come and tell you C6H14, I am quoting the molecular formula. Here's what we are going to do, right? I am going to take this same hexane and I am going to rearrange it. So I'm just going to use a different color so the change will be obvious. You see how in the original one, it's an unbranched alkane. I have 1, 2, 3, 4, 5, 6 carbons. Here's what I'm going to do. I'm only going to take 5. 1, 2, 3, 4, 5. And then I'm going to put a branch here and put 1 carbon here. I obviously have what? 6 carbons still, right? I think everyone can agree with that, right? I still have what? 6 carbons. I just want to draw it a little bit better, right? I just want to draw the branch a little bit longer. You'll see why just now, right? I still have 6 carbons. Now, remember the rule. All carbons must always have how much bonds leaving it? Do you all remember? All carbons in organic chemistry must have how much bonds attached to it. Not 3, it's 4. Look at it. I can prove it here. The answer was on the screen. Look at it. Look at this. I just say, look at this carbon here. How much bonds it have coming out? 1, 2, 3, 4. Any carbon you choose will always have 4 covalent bonds touching it. Always. If it doesn't have 4, you do something wrong. So I'm going to follow that, right? I must always have how much carbons, how much bonds coming out? 1, 2, 3. And this orange one here is 4, right? So for all of them, I have to do that. So let me complete this diagram. I have to make sure any carbon that we look at, it must have 4 bonds coming out, right? I like to use the different colors here. I'll use H here, H. At the end of each bond, we are going to put an H. Do I still have a, once I follow that rule that each carbon must have 4 bonds attached to it, and at the end of each bond I have a hydrogen, do I have the same amount of hydrogens and carbon as the original hexane? Do I have the same amount of C's and H's? Yeah, I think I guarantee you, if you count it up, right? I mean, you could, if you don't trust me, you could do it, right? You're going to get C6H14. I guarantee you, add up all those orange H's, you are going to get what? The same exact amount, right? Somebody said I forgot. Oh yeah, I did forget one H here. Sorry about that. Right, great. Now tell me something. Both these here, the original one name is hexane. Tell me something. Is the new one also named hexane? Will his name be hexane? No. But, so do me a favor. I brought this over from last week. Name this alkene for me, the new arrangement. What is the name of the new arrangement? Because in this one, we have a branch. And last week, I spent quite a lot of time showing you all how to name a branched alkene. The full name is not pentane. Guys, you have to follow this format here. Go back from last week, and naming a branched alkane is quite a bit of work, right? Right. Seeing plenty correct answers coming up. Take a half a minute. So what you have to do is look at the main branch first. This here is not the main branch, the main part of it. Let's call it the tree trunk. And then we have what? A branch. So this dash part here is the branch, right? So I dash the branch. So the main part, we use the red here. So the main part has 1, 2, 3, 4, 5, right? So 5 is what? Pent. I'll write the name up here. I'll have space up here. It's what? Pentene. So the main branch always ends with "ene" and it has 3 carbons. The branch itself only has 1 carbon. That's this blue part here. Remember, the branch always ends with YL. And since the branch only has 1 carbon, its name was, I wanted to put it in different colors. Its name will be meth. And all branches end with YL. The meth stands, minimum meth is 1. It means that the branch has 1 carbon, all branches end with YL, and the pink part is the main part, right? Right. Now, where does the branch occur? You have to pretend you're walking from both sides. If you start to walk from the left-hand side, the branch occurs at 1, 2, 3, 4. The branch comes off the 4th carbon on the main part. But if you walk from the other side, it comes off which one? 1, 2. You have to choose the smaller value. Okay, it's always the smaller value, right? Guys, so I have to make the assumption you revise a little bit, right? And come to class a little bit. Remember, I always tell you all that, right? Because if I had to keep one or two people are asking me to kind of go back through what I did last week because it was lost or it wasn't here. Obviously, guys, that's not fair, right? I spent a lot of time doing this last week. I can't just slow down the entire class because you missed class and you didn't review the recording. Or you didn't bother to revise a little bit, right? I have to finish the syllabus. All right, great. Right? And I think most of you all can agree are still not moving fast, are still moving at a laxed pace. Right? Great. Now, here's the thing. If you notice both of them have the same exact molecular formula, look at this. Hexane is called C6H14, if I am quoting the molecular formula. And 2-methylpentane has the same molecular formula. So let me just say it this way. If I send you to the chemistry store and I say buy some C6H14, and that's all the information I give you, will you know which one to buy? Think about it. I tell you go buy C6H14. You don't know which one to buy, right? So you see the limitation of the molecular formula. A molecular formula only tells you the amount of carbon and the amount of hydrogen, right? It doesn't tell you how the carbon and hydrogen are arranged. For you to buy the correct thing, I either have to give you the full name, I have to say, hey, go buy hexane, or go buy what? 2-methylpentane, or I could draw out the full structural formula. Now, if I draw out the full structural formula of the one I want you to buy, you know which one to buy, right? So I just wanted to point that out. You see these two, you call them isomers of each other. He's an isomer and he's an isomer. So isomers are just different versions of the C and H's being rearranged. Right? Now, obviously, hexane and 2-methylpentane will react slightly differently in the lab, right? Because they are two different compounds. You can't expect them to behave exactly the same. They must have a difference. Can I create another isomer? Yeah, and I can create another isomer. If you notice this branch comes off the second carbon, if I make it such that the branch, right, comes off here now, will it have a different name? Tell me something. Will it have a different name now? Well, I want you all to come up with a different name. Yes, it will have a different name. Well, what do you think the name of this isomer will be? He's just a different version of the 6Cs and the 14Hs in a different pattern. I know it kind of cramped here, right? It shouldn't be too hard to figure out what the name is, right? The main branch, the main, you know what I'm going to start calling it? You see the main part, I'm going to start calling it the backbone. Like that's a better name for me, right? The backbone. The backbone has 1, 2, 3, 4, 5. And people are just putting the answers on the screen already. It's coming up really fast. So it's still pent in because the backbone has 5. The branch still has 1 carbon, so it's still methyl, but whether you walk from the left to the right, you notice it will always be 3. 1, 2, 3. And if you walk from the other side, it's 1, 2, 3. So in this one, it don't matter which side you walk from, you get the same exact value. So you just use the 3. Right? It's not propyl, right? Matthew, you saw a mistake. The branch still has 1 carbon. Right? And of course, his molecular formula is C6H14. I mean, if you want, you can count it up. I guarantee you. So you see, if I send you to the chemistry store now and I say buy C6H14, you even have a worse problem now. It have 3 types of C6 what? H14. But I think you'll get the idea here. All of these are just different versions of the C and H's being rearranged. We call that isomers in chemistry. Right? So update your slides, put in everything that you don't have there, write it in exactly how I have it. Take 2 minutes, right? Listen. One H is missing. Let me put it in. Right. I hope you all do a better job than me at drawing it. When you have a drawing pad, it's be kind of hard to draw things real precise. Oh, well, I think you all deserve a small break there. All right, so let's see if you guys can get a little bit lucky here. So everybody gets to choose 3 letters, any 3 letters of their choice. I hope you get the tokens, right? Remember, like for example, the green team can only collect the jerseys, the green jerseys of it. Good luck, good luck. All right, let's see what you guys got. All right, let me know how much you were able to get. Right. Somebody got 0. Don't worry, if you got 0, keep your eye on the lady at the back table on the right-hand side. Keep your eyes on her. And it seems that she was going through her trash and she found a pink boxing glove, and a bandage. So I hope that helps somebody feel like 0. Sorry, you'll get better luck next time. Better luck next time. Um, keep track, eh? Keep track. All right, let's move on. So let's go through some reactions of alkanes, right? Let's say you buy an alkane in the chemistry store. You might be wondering, well, how does it react? Well, what's so special about alkenes? Well, here's 3 cool things about alkenes. One, alkenes burn in air or oxygen, which is good, right? Alkenes burn in air or oxygen. So that means alkenes can be used as a source of fuel. I'll give you a good idea of where you can find an alkane. Cooking gas. Everyone has a tank of cooking gas in their kitchen. Guess what it have inside here? An alkene. Now remember, it have many different types of alkenes. It have methane, pentane, hexane, butane. It even have branched alkenes. So you're probably wondering which one of the many alkenes are found in cooking gas. We'll get to that in a little while, okay? But just know, alkenes are a great source of fuel. Alkenes also undergo something called substitution reactions. I don't expect you all to understand what this is until I explain it, but I'm going to go on a hunch that you all know what substitution means. In a game of football, when you substitute someone, doesn't someone go on the field and doesn't somebody come off the field? Isn't that what a substitution is? Something goes on and something comes off, right? So that's all you really need to understand right now, and I will explain it in detail later on. And alkenes can also be cracked. Well, what does cracked mean? Basically, if you take a piece of stone and you hit it and you crack it, doesn't it form smaller pieces? So to crack something in, let's say, chemistry means simply to break it into smaller pieces. And you can do that with alkanes. You can actually take a big alkane and break it into a smaller piece. And I'll show you how that's done in a little while. Okay, so this is already on the slide, so I'm just going to move forward, right? Well, you're not going to get a chance to take down the notes, right? The whole point, like I said, is to fast track things. So alkenes are also called saturated. Now, let me explain what saturated means, right? You notice in alkenes, it only have single bonds, like all the bonds were like single bonds like this, right? Anytime in organic chemistry, you see something with single bonds, the fancy name for that, it's called saturated. If you see things with double bonds like this, like you see two bonds, you see what I have two bonds here? That's not saturated. It's actually the opposite of saturated. Take a guess. It's called unsaturated. But don't worry, I'm gonna mention that later on. Okay? So what we're gonna do, we're gonna discuss all three in detailed here now. All three. So let's move to the next slide. Right. Before you even read the madness that's on the screen there, when in most cases, right, on a brand new clean stove, not a dirty stove, right? On a clean stove, when you light the fire, what color is the flame? On a clean stove, eh? Not a dirty stove. It's always blue. I know sometimes you all see an orange flame. That is when your stove not clean and the pot on it not clean and all kind of thing, right? But just so on a clean one, it's blue. So one thing we mentioned already is that alkenes burn in what? Air or oxygen. And they always burn with a clean blue, we know this, non-smoky flame. When you light a stove just so, you don't put no pot on it. Does it produce smoke? Think back on it. See if you can visualize that. Let me say it go, right? It doesn't produce smoke, right? A lot of people think once you light a fire, it produces smoke. Not kitchen gas. If you light your stove and provided it has to be clean, obviously, right? It produces no smoke, right? Great. So that's one important thing about alkanes. Another important thing, it's clean, blue, non-smoky flame. And in the exam, they might ask you to write the formula for it, the balance equation of it burning. Anybody wants to tell me what's the name of this alkane? CH4. What's the name of that alkane? CH4. Right, this is, for my example, I use methane. Obviously, you can have a similar equation for ethane and pentane, but usually they ask you to quote the one for methane. So when you take methane and you add oxygen, remember, it needs oxygen to burn, right? It produces carbon dioxide. Carbon dioxide is colorless. Carbon dioxide doesn't have a color. It produces carbon dioxide and H2O, but you notice I put G. The G means it's steam, right? It's water vapor because it's so hot. The liquid water doesn't form on the stove itself, right? It produces it in the form of water vapor. And what does this mean again? Triangle H negative. It means it's an exothermic reaction. In other words, it produces heat, which is obvious because the flame is hot. Okay? So you need to memorize this equation for the CXC exam. Well, any chemistry exam, not just CXC, right? It could be Form 4, it could be Form 3. You need to know it, right? Everybody okay so far? The hardest part here is to memorize this. And I'm real sorry, guys, but you see, organic chemistry, you're going to have a lot of things just to memorize. All right? So you're going to have like over 50 things. I'm not lying to you. 50 things. Equations you're going to have to memorize. Okay, so prepare yourself, guys. Prepare yourself. All right, so let's move on, guys. Let's move on, right? Let's move on to the next slide here, right? It's not my fault, guys. Believe me, if I could have a little word with CXC with making the syllabus shorter, I would. All right. All right. So let me show you what's going before we move to the next slide. And I'm going to divide this into two because they can look intimidating at first. Anybody wants to tell me what's the name of this alkane? Take a guess. What's the name of that alkane? A C with 4 8. Yeah, it's methane once again, right? So you have methane. Once again, The example could be with ethane, it could be with pentane, but most textbooks will just do a simple example with methane. Here's what we're going to do. We're going to take alkenes and we're going to start adding halogens again. Remember, halogens are in group 7, and the halogens are things like chlorine, fluorine, iodine, and bromine. So we're going to take methane. I'll write it just to make things easier. And we're going to add what? Chlorine. Remember, chlorine is diatomic, right? And 2 chlorines are bonded together. Well, what kind of bond do the 2 chlorines, like if you have 2 chlorine atoms, this bond represents the bond. What kind of bond do they have? Ionic, covalent, or metallic? How is Cl2 bonded? How is the 2 chlorines bonded together? It has to be covalent. Remember, covalent bonds is between non-metals. If you have 2 chlorine and 2 of them is non-metals, so that's a covalent bond in between. Now, here's what's going to happen. You have 2 chlorines here, and you're mixing it with methane. What's going to happen? One of these chlorines is going to kick out one of the hydrogens. It doesn't matter which hydrogen. It's just going to kick out one hydrogen, and the hydrogen is going to take the place of the kicker-outer. Yeah, that's not a real word. Okay? Right? So, you notice in a situation like that, that's a kind of substitution. Like, if you were methane, chlorine substitutes itself here and kicks out who? Hydrogen. Look it over here, guys. Take a look at what happens. You notice over here you have chlorine now, and over here it has hydrogen, right? It kind of like, yeah, it kind of like they switch places, right? They switch places. But yeah, I want you to think of it as a substitution. One of the H's was substituted in methane. Now keep your eye here. Let's say that this now goes over here, right? So he floats over here. Remember, he has 1 chlorine in him. And some more chlorine. This is a different chlorine, a brand new Cl2 molecule walk up to it, right? And he says, well, what do you all think is going to happen? Isn't this chlorine going to try to kick out one of the hydrogens? In other words, it's going to repeat the behavior. And look what happens in the next one here now. Now might have 1 chlorine here. Look what happened here. It have 2 chlorines now. This hydrogen get kicked out to join the Cl2. Well, what was Cl2? So you notice you start off with 4 H's, no chlorine here. And then you have 1 chlorine. Then you have 2 chlorines. Do you all see a pattern here? If we put more Cl2 and the chlorines gradually kicking out all the hydrogens, it's like the chlorine is a disease. And anytime it's a takeover, that's the better word. It's a hostile takeover. Eventually, how much chlorines do you think it will have in what used to be methane? How much chlorines are we going to end up with? 4, but that's the maximum amount, right? It will never kick out the carbon. It's only on a mission to kick out the hydrogens, and it does it one by one in a substitution manner. Okay? Now, tell me something, right? I'm gonna clear everything here. If the first one is named methane, right? Do you think when 1 hydrogen is kicked out and replaced by chlorine, do you think we still get to call it methane? Or do you think the name will change? Right? The name will change, right? And of course, when it have 2 chlorines, the name will change more. And when it have 3 chlorines, the name will change again, right? Right? Now, someone asks why the hydrogen is kicked out. I really don't know. I never even really question it, right? All I know, the hydrogen is just kicked out, okay? Now, you don't need to take down anything here, right? But I think you all get the concept. The amount of hydrogens is getting less, and the amount of chlorines is getting more on the methane. One by one. Like somebody said, it's a takeover, a gradual takeover. I want you to look at the next slide and tell me if you see that happening. Yes, you need to not memorize, reason out these four equations. Look at it. This is a more simplified version. Look at it here. You start off with methane here, regular boring methane. C and four H's. It mixes with the chlorine. You notice what happens after? You only have three hydrogens and one chlorine, and then you get HClG. Because remember, the one chlorine joined the Cl2. Then this CH3Cl decide to run away. It's like, oh God, they're taking away all my hydrogens. But then it bounces up a next chlorine. And look what this chlorine does. The chlorine goes, he has three hydrogens. He takes away one, and now he has two hydrogens and two chlorines. And then he decides to run away. So, oh God, they're taking away all my hydrogens. And he bounces up a next chlorine. And it has three chlorines and one H. And eventually, the last hydrogen gets taken out. Yeah, he's not learning. He's a slow learner. Can you all see this? I need for you all to see this, that as we go downwards, the H's are slowly getting replaced by chlorine, right? Now, the same thing would happen if it's bromine, right? Instead of Cl2, if it's Br2, the same exact thing will what? Happen, except you just put Br instead of Cl. Now, like I said, the names will change. The original one is what? Methane. When it has one chlorine, right? When it has one chlorine, it's called chloromethane. When it has two chlorines, it's called dichloromethane. When it has three chlorines and one H, its name is trichloromethane. And when finally all four hydrogens get replaced with the four chlorines, it's called tetrachloromethane. Okay? I needed to add in the arrows for me. Whatever extra I wrote on the slide, please add it in. It's a simple. At first, this looks intimidating, huh? Because when I now switched over to online classes, and when students first saw that, right? They freaked out. And how much of you all were getting a little bit freaked out by just looking at it? But after the explanation, you realize, wait, no, there's a pattern to all of this, and it's not really that difficult, right? Right? It's all bark but no bite. All right. Think you all deserve a little headrest there. All right, so have some favoritism here. Let's see. The green and blue teams get to pick two bags. So you have three bags to pick from, right? Blue, green, and white. Now, the color of the bags have nothing to do with the team colors. It's just hard to get colors, right? So green and blue team choose two colors of bags. Unfortunately, everybody else only gets to pick one bag. Wish you the best. What? Three people on six. Oh, and one person on seven. I wonder if there's some extra. Oh, and somebody if you look on the right hand side there, somebody found this on the ground. A guitar, a glove, and a band-aid. So I hope that helps you all too. Eight. Somebody on eight. Right. Now, here's the thing. Remember, I told you the two things alkanes can do is be cracked, meaning that you can break it into what? Something smaller. Now, it doesn't break, in most cases, it doesn't break into two equal pieces. And it's not, it's a kind of strange way it cracks into two pieces. So let's say that you have something called heptane. Heptane has obviously, remember, means 7. If you look at the table, 1, 2, 3, 4, 5, 6, 7. And it follows the formula, C7H16, right? Believe me, that is an alkane. What they usually do in factories, if you take heptane and you apply plenty heat and plenty pressure in the factory, you notice it break it into two pieces. Look at it. But this piece here looks what? Normal. It has how much carbons? 1, 2, 3, 4, 5. And it only have single bonds. So we know for sure this is pentane. Remember, we start off with how much? 1, 2, 3, 4, 5, 6, 7. And we have 1, 2, 3, 4, 5. But then it breaks up into a second piece. But the second piece has a double bond. We haven't done anything with double bonds as yet. Anything with a double bond is called an alkene, which we have not done as yet. And it's the next topic that I plan to do. So it's a nice setup for alkenes. Okay. So anytime you take an alkene and you crack it with heat and pressure, it always breaks up into a regular boring alkene, and it will break up into an alkene. That is how it breaks up, right? And this is a very useful process, right? So just adding what I put in there, and we'll move on to the next slide, right? This is, right? You all are going to see the usefulness of being able to crack an alkene, break it up into two pieces, an alkane and an alkene. But later on, not right. Right, so let's set the stage now. You notice the monster is asking, what is that double bond thing about, right? Right. Oh, one more thing. There's one more thing, right? More uses and properties of alkenes, right? Now, here's the thing. Not all alkenes are gases. Remember, I just said that you can find alkenes in your kitchen as a cooking gas, right? Some alkenes are gases, obviously. Some are liquids and some are solids. Now, anytime an alkene has 1 to 4, these values here represent carbons. These, I'll put a little arrow here. These things represent the amount of carbons. So if an alkene has from 1 to 4 carbons, things like methane, ethane, propane, and butane, they will be what? Gases. If it has from 5 to 17 carbons, it will be what? A liquid at room temperature. Everything here is room temperature and pressure. And anytime it have more than 17 carbons, right? 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 Anytime it have more than 17 carbons. Well, they'll never ask you to name those, obviously, right? You just have to be able to quote it, right? Anytime it have more than 17 carbons, it's a solid. Now remember, this is at room temperature. If you are doing another question, right? Like say something and you see something with 1 to 4 and it's not a gas. And it's not a gas. That means probably that experiment is not taking place at what? Room temperature, right? This carbon, liquid, and solids is for room temperature. I believe room temperature is about 27 degrees Celsius and 1 atmospheric pressure. And all alkenes are colorless and odorless. So that means if you have an alkene in the room, you're not going to be able to smell it or see it. They're very sneaky. They're like ninjas. All right. Okay. Right. And here we have some uses of alkenes that you got to be able to quote one or two for the examiner, right? So just read through everything here, right? Just make sure you understand it and we will move on, right? It's nothing much you have to add in on the slides here, right? Right, now we move on to the alkenes, evil twin alkenes, right? Which I never realized was something different from alkenes because I wasn't good at chemistry in high school, right? So I wasn't even aware alkenes and alkenes were different. Sad to see. All right, great. Alkenes have a different formula, but it's obviously spelled slightly different. And remember, alkenes follow the formula CnH2n plus 2. Alkenes don't have this plus 2 here. It's only CnH2n. It have no plus 2. And they also have a double bond. Look at all of these diagrams here. All of them have a double bond somewhere. Don't worry, it's only going to have one double bond for the CXC syllabus. Yes, in Form 6 chemistry, it have more than one pair of double bonds, but this is CXC, right? Only one double bond. And for all of them, you will realize that it follows the formula. I can prove it here. The first one has how much? 1, 2, 3, 4. If I have 4 carbons, then according to the formula, I'm supposed to have how much hydrogens? 2 by 4 is 8. Count it up. 1, 2, 3, 4, 5, 6, 7, 8. And also, any carbon you pick has 4 bonds. Look at this guy. If we pick him, 1, 2, 3, 4. If we pick him, 1, 2, 3, 4. Right? You gotta be real careful, right? Even if we choose this last carbon here, he has 1, 2, 3, 4. Right? Alkenes end with ene, obviously. If it has 4, 1, 2, 3, 4, his name is butene. If he has 1, 2, 3, 4, 5, his name will be pentene. Oh, there's a little problem though, right? And I'm not saying it wrong, right? Butene and pentene is actually correct, right? But if you want to be, it's a good idea to specify where the double bond occurs. And you have to put the shortest route. If we walk from this direction, where can we first access the double bond? 1, 2, 3. And we can just stretch our hands here and touch the double bond. But if we walk from the other direction, and once we jump on the first carbon, we can stretch our hands to access the double bonds. It's a good idea to always state where the double bond occurs on the structure. And you always have to show the shortest path. So the official name for butene is 1-butene, meaning that the double bond is accessible from the first carbon. And the next one here, if we walk from this direction, it's also 1-pentene. But whenever it's 1, most people don't put the 1. The 1 is understood. Now, there are 2 ways to write it. Some people put 1-butene or but-1-ene. And some people may write it like this, pent-1-ene. For those who are in school, well, which way does your teacher prefer? The one on top or the one underneath? Where the number is in the front or where the number is in the middle? right? And everybody's going to be mixed, right? You could choose any one. I know some teachers going to use the one on top and one underneath. I am a fan of the one underneath, where the number goes in the middle. Okay, great. Right, most texts you'll realize I don't really have a reason for it, right? Which one I prefer. It's just that I realize the older textbooks use this, but the newer textbooks just use the one in the middle. So I'm going with the newer one to be more modern. All right. Update your slides, guy. Update your slides. Everything that I just wrote, add it into your slide. All right, so I think we named these here already. I already named it for you guys, and I think you all understand the concept here already, right? So the first one was one butene. I should have leave it for this slide, right? So, right. So I just say if, right? If for the second one I put the double bond over here. So I move the double bond to over. I know if I move the double bond, I'm supposed to rearrange the H's, right? Let's show you how it would be a rearrange. If I move the double bond here, you notice how much bonds leave in the C? 1, 2, 3, 4, and 5. Can I have 5 bonds leaving a carbon? No, I'm only allowed to have what? 4. So that means I'm going to have to scrape off one of these hydrogens and I'm going to have to put it somewhere here, right? I have to move it now, right? And for this carbon, I have 1, 2, 3, 4, but I have a little problem. Look at this one here too. This carbon now still has 1, 2, 3, 4, 5. So I'm going to have to scrape him or one of the hydrogens off, any one of them, plus the bond, and I'm going to have to move it over here. If you look at it now, any carbon you choose will have 4 bonds coming out of it. So alkanes, you just have to make sure now that if you move the double bond, what's going to happen? The H's are going to have to rearrange themselves so that each carbon has 4 bonds coming off it. Who can tell me what's the name of that alkene? And we know it's an alkene because between a pair of C's, you see a double bond. By the way, since it has a double bond, it's called unsaturated. It's no longer called saturated. Saturated is when all the bonds are single. Now, remember, if you walk from this direction, you can access the double bond at the second carbon. If you walk from the other way, it's accessible after the first, second, and third. You have to use the shortest route. So for me, I'll put it 2 ways. It's either you put 2 pent in or pent 2 in. Anyone is correct here today. Right. So if you can adjust your diagram on the slide, feel free, right? I'll give you like a minute to adjust it to put in that name. So don't worry, I have a little brain relaxer now. All right, so let me see how to play this game. You have to say 2 things, right? You have to choose any letter in the alphabet and any number from 1 to 20, 1 and 20 included, right? So you're choosing a letter and a number. And once the number, or every time your letter call, you get how much? 5 extra tokens. And if your number call also, like we say, you happen to get a number also, you also get 5 extra tokens, right? You don't have to get the 2 at the same time. Once you get your letter or the number, and if you get a letter and a number, well, that's better. That's 10 tokens. You read one, 19 and R. So I hope someone at least picked 19 or R, right? The next ball is 5 and 8. So if anybody picked 5 or 8, you're getting 5 tokens. 10X. The next ball is 17 and T. 1 and K. And the last ball, 8, D or C. Right? I hope either your number. Remember, someone asks if you get a number and a letter, you get 10. No, guys, for each correct one you get, 5 tokens. So let me just say your number was 17 and 17 total. You get 5 of your tokens, right? So right, let me know your total. Let me know your total. Right. Let's draw an isomer of alkenes. Now, this used to be hard, right? Where, remember what an isomer is? This is when you what? You just take the C's and H's and you rearrange them like it have a different pattern. So quickly, well, I think everyone knows the name of this alkene, and we know it's an alkene because it has a double bond in between the C's. So it has 1, 2, 3, 4, 5, 6. We could all agree that this is hexene. Well, more specifically, it's because the double bond comes off the first carbon, it's 1 hexene or hex 1 ene. We're all in agreement that the name of this alkene that I gave you is hexene. What if in the exam they ask you to draw, right? If in the exam, if they ask you to draw an isomer, for the CXC exam, for an alkene, if you change the position of the double bond and arrange it, and arrange the H's, it will be considered by an isomer. So if I take this one, 1, 2, 3, 4, 5, 6, right? Because I changed the position. Now, you can't put the double bond on this end, because if you put it on this end, if you walk from this direction, you will still access the double bond via the first carbon, right? So don't put the double bond over there. You could probably put it over here. So I'll put it over here. If I put the double bond over there and I rearrange this, right? I'll be real careful with my rearrangement here. I have to make sure every carbon has 4 hydrogens coming out of it. Sorry for the little cluster here. What would be the name of this alkene now? Anybody wants to tell me the name of this alkene? Notice every carbon has 4 hydrogens coming off it. Choose any carbon. And you know it's an alkene because of the double bond. What's the name of that alkene? Right, and real people have it correct. It's 3-hexene or hex 3-ene. And you notice the molecular formula for 1 hexene is what? C6H12. And the molecular formula for 3-hexene is still C6 H12. Sorry, tie down there, guys. My bad. Right? You notice it's the same thing. Once again, the molecular formula is kind of useless because once again, if I send you to the chemistry, no, not store, the chemistry store, and I say by C6H12, right? And you know, obviously it's an alkene I'm talking about because the formula fits, right? It have twice the amount of carbon. You won't know which one to buy. You're not going to know whether to buy 1-hexene or 3-hexene. But if I tell you the exact name, 3-hexene or 1-hexene, or I draw out the full structural formula, you will know exactly which one to buy. Now, because both of them have the same exact amount of carbons and hydrogens, they are isomers of each other. It's just that the double bond is in a different place. Now, quick question. Do you think it have something called branched alkenes? Just like how it had branched alkanes? Do you think it would have something called branched alkenes? Yes, right? Because what you could do instead of drawing 1, 2, 3, 4, 5, 6, you could probably draw 5 and a branch coming out. It will be a little bit more complicated, right? But here's the good news. They take it off the syllabus. So you guys have it easy. When it comes to isomers of alkenes, all you need to do is change where the double bond goes. And if the name changes, it's considered an isomer. So you guys have it easy, right? In my days, yeah, you had to know all of it. Isomers, right? I just did this one. This here is the diagram that I just drew, right? So that is 1, 2, 3, 4. Yes, 3-hexene. So you don't need to take that down. You just drew that. Now here's the thing. Alkenes, just like alkenes, undergo certain type of reactions, right? Just like how alkenes had 3 types of reactions. Alkenes also burn in air or oxygen. Alkenes, however, don't undergo substitution reactions. It undergoes something called addition reaction. So adding this word here. An addition reaction is not the same thing as a substitution reaction. Substitution is where one goes in and one comes out. An addition, you're going to see in a little while, is much different. And on the screen here, we have the first thing, alkenes burn in air or oxygen. However, right? However, when alkenes burn, they don't form a nice blue clean flame. This is where you get a yellowish flame, right? You get a yellowish flame and you get smoke. So fuels are not like for gas, right? For a gas tank, you're not gonna put an alkene in it because when you buy the gas and you light it, you'll get a whole lot of smoke in the kitchen, right? You only put alkenes in cooking gas, not alkenes. And this here is the balance reaction. Here we have ethene, and you add oxygen and you get carbon dioxide, H2O vapor, well, water vapor and gas. Now, in the exam, right, I see that asked this question already, right? If they ask you why it is get a smoky flame and not a clean flame, it has to do with the ratio of carbon to oxygen. You see all of this black dust you see in here? This is carbon, right? That smoke, that black smoke you're seeing is actually carbon in it. It's like excess carbon. Let me give you an example. If you have an alkene and an alkene, if I have an alkene C2, then it will be what? 6 H's. If it's an alkene, if you have 2 carbon, you have only 4 hydrogen, according to the general formula. What's the ratio over here? Isn't the ratio 1 to 3 here? Because 2 could go into 6 3 times. And what's the ratio here? 1 to 2, right? You notice for every 2 hydrogen, you have 1 carbon. But for alkenes, for every 3 hydrogens, you only have 1 carbon. And over here, the amount of carbon is more concentrated. You have more carbon per hydrogen. Just come like for every 2 hydrogens that come to a party, it invites 1 carbon. And for this one, for every 3 hydrogens that come to a party, you have what? 1 carbon. For alkenes, the ratio is actually higher in favor of the carbons. So that's why when you burn it, it does have like excess carbons, right? It does have too much carbon, right? It's not diluted enough. You can think of it like that. And that's where the smoke comes from, okay? But for the exam, I want you to memorize this phrase for me. Please memorize this when the question comes. Just learn it off and your life will be very, very simple. Okay? Right. So all I need to do for this one is just, you don't need to take down, I guess you can take down this if you want to add in this, but you have to take down this and put in the word ethene here. And you're good to go. Right. Now here's a general example. Let's say you have, and this always be alkenes. I made a mistake here, so let's update here. Alkenes undergo addition reactions. So let's put in that little adjustment now. So here we have an alkene. His name is actually ethene because it has 2 C's and all alkenes end with ene, and you can clearly see there's a double bond there. And any carbon you choose has how much bonds? 1, 2, 3, 4, touching it. Even if I choose this carbon, has 1, 2, and 2 coming out here. So let me just say we take ethene and we decided to mix it with something that has 2 parts, right? A A and a B part. Now, usually, if it was a substitution reaction, the A would kick out one of the H's and the H's would take the place of the A. Now, if it was a substitution reaction, but I now told you, alkenes don't really undergo substitution reactions. They undergo addition reactions. So when the ethene meets A and B, the ethene is like real, how you call it, like real welcoming and whatnot. He say, A and B, you all look lonely. Do you want to join our party? And they make space for both A and B. They take A and B and add it into their structure. So let me show you how this works. You have to imagine it like this. You all see the double bond here. I want you to pretend that the double bond, the one underneath, disappears, right? And this bond here is going to split into 2 bonds. So the one bond that disappears splits into 2 bonds. So that's how I want you to use the imagination. And I want you to imagine all the H's straighten out itself, right? This H goes more straight like this. This H comes over here. This H straightens out here. It can straighten it out anyhow, right? And you see this bond he breaks up into two bonds, 1 and 2. And guess who gets attached to these two bonds? Remember, A and B gets pulled into the structure. A goes here, B goes here. It doesn't matter if you put the B here or the A here, right? You see what happens? The A and the B get pulled into the structure. It's accommodated within the structure. It's added in to the structure. So that's why you call it an addition reaction. And you notice after the reaction, right? No more double bonds exist. So after an addition reaction, you get no more double bonds. In fact, it seems to more resemble an alkene now rather than an alkene. And you're going to realize that a lot for alkenes. Alkenes, after the addition reaction, tend to tend to resemble alkenes after the addition, right? So everyone take down this, right? The H's could be arranged anyhow. Like what I was saying, the two H's could be over here, and the A and the B could be on the end, right? It doesn't matter. It's actually kind of random of the positions of the A and B after. But most textbooks just put it in at the bottom of the structure. That's just their preference. No good reason behind it, right? Once it's there, correct. All right, so we have a little which team is the best? Which team do you all think is the most popular team here today? Now, I know everyone here chose a team at the beginning of class. So we're going to do our class votes, right? This is supposed to be an MMA match here, right? Which is supposed to represent the blue, team blue there. But let's go. Let's take a poll, guys. Team color. All right, vote for your team. Let's see which team is the most popular. The most popular team gets 5 extra tokens, and the second most popular gets 3 extra tokens. All right, so I ending the poll there, and I'm going to share the results. Take a look, take a look. First place goes to Team Blue. So everybody in Team Blue, you get 5 extra tokens, okay? And Team Pink is second place. You all get 3 extra tokens, okay? All right. I honestly thought Team Yellow was going to be the most popular, right? That was my thoughts when I made this game. But apparently, Blue and Pink are the winners today, right? I have a good feeling a lot of guys didn't vote, which led to these results. All right.